Hi guys, welcome to the next session on this AMJ 40103. So this is the next topic. The next topic we want to discuss about joints and tolerance. So basically, in this topic, we need to emphasize more. There will be a more emphasis on design work, but the topic will start more on the fundamental of the design. So joints and tolerance. So it is important, joints and tolerance, because the design and construction of joints and connections transmit the forces from members to members, component to components, from beam to columns. So ensuring the forces are being transmitted from top floor towards the foundations, and ensuring the stability and robustness of the structure that we are designing. So there are various methods: bolting, welding, grouting, or just simply place just to ensure that the component in contact. There are various methods to produce a joint, but they must be simple and clear for site operatives to ensure the effectiveness of the joints. And a joint should resist both serviceability and ultimate loads, as well as abnormal loads, but there is still lacking information on abnormal loads, the effect of joints, and how joints perform under load from abnormal loads such as fire, impact, explosion. But uh, we are currently designing for serviceability and the ultimate loads. And a joint failure should never lead to structure instability. So the aim is to transmit the load. Should the joint fail, the there should be it won't it should be designed to not lead to structure instability. So it is important to distinguish between joints and connection. So joints is the interfaces where forces act between structure elements, often involving intermediate materials. So you have forces acting, can be tension, shear, compression, and you have intermediate materials, for example, rubber, steel plate. But the connection is the assembly where forces and moments act through multiple interfaces. So that is the difference between joints and connection. So joints is the interface, connection is uh, the item itself. Joint is the interface. So in design consideration, connection design must account for fire hazard, accidental damage, temporary construction effects, workmanship accuracy, and durability. So we're gonna go through this in the design. Additional forces unique to a precast structure are generated owing to relative displacement and rotation between elements. So there's a extra unique forces that is generated due to displacement or rotations between the elements. So some of the, for example, beam, they have end rotation, so there's additional forces there. So you need to design for that forces also. So this is an example of the fill material and the components, as you can see here. When you have a component of column here, example, so you have a force transmitting from top to bottom, so you have infill material. So if the infill material is having strength, elastic modulus lower than the elements itself, so you will have a material that will deform under load and would cause a tensile splitting crack on the components. But you have the infill. If the infill, the grout, neoprene rubber, or other bearing materials that has greater elastic modulus than the precast component, there will be a localized crushing. There will be a concentration of load. from top to the bottom, there will be a concentration of load on the bottom component, so it will cause a localized crushing. So it is important that the infill has same elastic modulus and strength as a precast unit. So it will be the trajectory of load will be uniform from top to bottom, as you can see the trajectory here of the load. And also as you can see here, this is a compression, the joints. This is the joint area. So as you can see, you need to design, although the joint that you are seeing here, the tension and shear joints here, you have shear joints and then tension joints, and then this is a compressive stress zone. Although the action are mostly at the end of the component, for example this beam, at the end of this beam, but your design should be uh, between 1.5 to 2.0 of the height of beam. So you need to design the stirrup up to this length. So basic mechanism. First one is basic mechanism. What is mechanism? An action of forces between structural elements. So there will be action of forces. So it is important to differentiate the component based on the mechanism. The mechanism, the action of forces, will distinguish between the monolithic cast in situ versus the side jointed precast member. So in the precast element, so you have a isolated precast element and non-isolated precast element. So isolated precast element is the elements when the elements is connected to other elements with no secondary means of load transfer. So there is no alternative means of load transfer. So if the method of transferring the load fail, so it will cause a total failure. But for non-isolated precast elements, the elements are connected to other elements with a secondary means of load transfer, which would sustain loads in the event of failure in the primary support. So you have extra means of load transferring. For example, if it is isolated precast element, is a stair flight. A stair flight unit seated on a dry core bell is an isolated element. So if the end section of a stair flight is fail, then the element will fail, and the stair flight would fall down, would experience a failure. But in example for non-isolated precast elements, the example of a component would be a hollow core flooring units, which are grouted together between the floor, and then in the event of a failure at the beam support, and the adjacent floor would support the neighboring floor, so that even though the beam failed at that section, will still be attached to the adjacent floor. So that is an example of non-isolated precast element. So it helps you categorize the type of elements of precast. So simple rules on design of joints. So concrete cover outside reinforcement is ignored. So you're not designing the area of bearing. The length of bearing does not include cover. An allowance for construction tolerance should be 15 mm for 6 meter long. You go 7, then add 1 mm, then add 4 mm. So for 10 meters long, 10 meters long beam, so you would allow for 19 mm of allowance, manufacturing defect. So this is your allowance tolerance. So what happens is that it affects your bearing length here. So it will reduce if you increase your allowance, so you will reduce your bearing length. So in the end it's bearing area, and then you increase. When you reduce the area, you increase the force, increase the pressure. So your design will be more heavy. It's me. If horizontal forces is larger than vertical forces by tan 20 degrees, so lateral reinforcement in the top of support member or continuity reinforcement to prevent spalling in the support member is provided. So you need to provide uh, support. Effective force transfer, the angle, so this theta should be not less than 30. It should not be slanted more, but more than 30. So there's load being transferred from here to your core bell, for example in this photo. Anchorage of ties, full anchorage of ties by mechanical means must not interfere with compressive stress regions. And the pressure zones in couple joint must actually 0.9 times the net of depth of section. So pressure zones 0.9 B. So this is the photo. So your anchorage of ties must not interfere with compressive zone. So this is your anchorage of ties must not interfere with the compressive zone. So your ties should not be in compressive zone. And then pressure zones in coupled joints must not exceed 0.9 times the net depth of section. So this is your compression zone should not exceed 0.9 depth. 0.9 depth of the section, and these are shear friction joints not to be used in isolated elements or situations where direct elements may develop without a tensile tie. So your friction joints, shear friction should only be used in non-isolated elements. So a compression joint. So next, we want to start designing. So first one is compression joints. You have compression joint, tension joints, moment joints. So the first one is compression joints. So compression joints, types of compression joints will be bearing in plain concrete, and then designed for bearing in plain concrete, and then concentrated loads in bearing. When you have a concentrated loads, then reinforced and plate reinforced concrete bearings designed for bearing on component that have reinforcement, and plate reinforced, plate embedded within the concrete, and then a bearing pad. When you place a bearing pad on top of your components to sustain the support, to support the compressive force, the bearing pressure. So types of bearings you have. The first one is dry bearing of precast to precast or precast to in situ concrete. So nothing there, just precast to just a component to component itself. And then you have dry pad bearing where you put some shim gap. So when you put gap, when you place your component and then you inject grout. Then second one is bedded bearing, where the elements are positioned onto the semi or wet sand or cement grout. You put a semi wet sand or cement grout on top, so that acts bearing. Or you use elastomeric or soft bearing like rubber, neoprene rubber or similar bearing pads. You put material, usually they use rubber on top of your component, as in this example. And then extended bearings, where the temporary bearing is small and reinforced in situ concrete is and reinforced in situ concrete is used to complete the connections. So a temporary bearing is placed, and then you cast the bearing, you cast the bearing. Then bearing also have reinforcement, and then steel bearing using steel plate or structural steel section. You put uh, structure steel, for example in here is a combination of structure steel and then steel plate, and then you have another bearing here, so it adds up onto your strength of your compression joints. So bearing in plain concrete is used where bearing is uniformly distributed and the bearing stress is low. So you don't have any reinforcement on your bottom component. So typically your force, maximum bearing force should be less than 20% of your concrete strength, or compressive uniaxial compressive strength, or up to 30%. Let's say you have a 50 grade concrete, so 30% of 50 is 15. So that is your maximum bearing force. So if this complies, and you don't need any bearing, no reinforcement is required. So the ineffective bearing width, so you want to calculate the bearing width. So the ineffective bearing width, i.e. allowances for spalling, given in table 4.4. So this is table 4.4. It depends on your method of support, and then gives you the ineffective bearing weight. So example, if your method of support is steel, so there is no ineffective bearing weights. But if your concrete is grade lower than 30 megapascal, so the ineffective bearing weight is 15. So you need to minus that, reduce your bearing weight by 15. If it is a grade, if it is more than 30, if it is less than 30, or it is a masonry, you use take up your brick by brick, so your ineffective bearing weight become larger lah. If it is a reinforced concrete less than 300 mm deep at outer edge, so your nominal cover to reinforcement at outer edge, so basically your cover, and so on. At supported, this is so for the top one is for supporting member, so the bottom one, and the top one is the supported member. It depends on your design. So let's say you design for a column supporting a beam, so ineffective bearing weights you will be calculating based on this supporting member, and that beam is based on this supported member. So if the beam is a reinforcement at bearing of supported member, if the tendons or straight bar exposed at end of member, so there's no ineffective bearing weight. So basically, if you have a post tension or pre-stressed beam, so the tendons is exposed up to the end, so there will be no ineffective bearing weight, so you don't need to minus anything. But if it is a simple beam, straight bars, and horizontal vertical loop, so you need to minus 10, and so on, and go through here. And so you want to calculate FB, FB basically. So you can get your FB from this top here, and you put it here, so you can calculate your effective bearing length and net bearing width, or you can start from here and then check back here. You can start from this equation here, but the effective bearing length and net bearing width, the net bearing width is influence, is the relate with your ineffective bearing width. Depends on your type of components and reinforcement and so on. So the only additional bearing stress condition to add to the list, appropriate to isolated beams and column bearing. So if it is a isolated beam and a column, so your steel bearing of size BP, so this is your width of bearing, steel bearing, cast into member or support and not exceeding 40% of the concrete dimension, B 0.8 FCU. So at the edges of the steel bearing should not extend to a distance equal to spalling allowance. Higher bearing stresses may be used only if approved by adequate testing. So for larger bearing plates, the allowable bearing stress is given as follows, this equation. So let's say you have a steel bearing embedded into your column supporting the beam. So you can so the allowable bearing stress will be calculated by this equation. If you don't have any if you don't have any support reinforcement, so this is your equation for ultimate bearing. So this reduced stress is to cater for diagonal tension directly beneath the insert close to the face of the outside face of column. And in calculating compressive strength, the area of concrete or mortar filler in horizontal joints between load bearing walls and our columns for solid flow onto the beam should be greater of the area of the in situ concrete, ignoring the area intruding the element, but not greater than 90% of the contact area. So within 90%, less than 90%, so that should be your bedding, and 75% of the contact area. So if the beam is smaller than the column supporting it, so the contact area will be based on the beam, and the area of concrete or mortar filler should be greater than 70% of the contact area. This is some clauses. So when you're specifying your bedding or bearing size, so this another two additional clause to be followed. You need to be 75% larger than contact area, and then larger than the area of the in situ concrete, but not greater than 90%. So you can based on the contact area, but you play around within 75 to 90%. So let's take a look at example number 1. So this is the this is example of a plain bearing. So there's no reinforcement. So basically the bearing force very low. So the question is, example 8.1, calculate the load bearing capacity of a 6 meter. So you have your dimension here, the length of 6 meter by 1.2 meter. 6 meter, 1.2 meter, 1.2, 6 meter. Hollow core unit supported by a precast beam. So your slab is supported by beam. The nominal bearing length given to you, your nominal bearing length. So this is your B, your bearing length, nominal bearing length. The hollow core unit is grade 50, so you have your FCU here. FCU. And the tendons reach to the ends of unit, so this gives you clues for your ineffective bearing width. So the beam is grade C40, so the supporting member is grade C40 and more than 300 meter deep. So this is 300. The beam is 300 millimeter deep. So ignore any horizontal friction forces. So there's ignore the horizontal forces and assume that the hollow core unit is otherwise tied to the beam. So how do we solve it? So the design ultimate bearing stress, which is based on the cube crushing strength of the weakest of the two or three component material. So in this case we have two. So for dry bearings, this is your design ultimate bearing stress, 40% of the weakest of the two cube crushing strength. So the weakest will be 40, and for if you are designing for wet bedded bearings on concrete or mortar, it's 60% of your compressive strength. And then if you have a elastomeric bearings, so between 40%, 0.4, 0.6, so it is suggested to use 0.5, 50% of your compressive strength. So the ineffective bearing width allowance for spalling are given table 4.4. Need to highlight here that it is reproduced from BS 8110 part 1. So as you can see here, your supported member is tendon exposed at end, so 0 ineffective bearing width for supported members. For supporting members, it is a grade more than 30. So here is your ineffective bearing width. So solution, ineffective bearing length is 15 mm in beam and 0 in floor unit because of the tendon extend up to the end of the slab, and a clear distance between support faces is 6 minus 0.075 minus 0.075. This both is nominal length, nominal bearing length. So basically the floor, the hollow core slab is sitting on 5.85 clear distance between support 5.85. Also we need to minus the constructional inaccuracy, as we said before. For 6 meter would be 15 mm, so 15 mm. So net bearing width, your slab is placed at 75 mm minus 15 for this delta constructional allowance, minus 0 for the ineffective bearing length, and then minus 17.6. It's 17.6. So the 17.6 is it's from this no, actually 17.6 is the constructional inaccuracies, but the 15 is from this ineffective bearing length of the beam. So this is for beam, this is for slab. We need to minus them all from your nominal bearing length. So you get your 42.4 mm, so which is larger than 40 mm. So your nominal, your net bearing width should be more than 40 mm as specified by the BS. So it need to be more than 40. So if it is less than 40, so you need to stick to 40. So you need to adjust your sizing for contact length lah. So effective bearing length is the least of actual length, i.e. width of hollow core unit. So you need to check what is the least length. So for hollow core unit, which is the dimension is 1200 times 6 meters. So this is 1200. So divided by 2 plus 100. So you get 700 mm. So the effective bearing length. So for effective bearing length, this is length, this is width. So you already have your width. So now you are looking for your length. So your length is basically supported by the beam. So this is your slab. So this is your net bearing width is 40. So your effective bearing length should be least of the actual length, or the half of your slab plus 100 or 600. So there is 3 measurement that you need to consider when determining your effective bearing length. The actual length, or the half of your slab component plus 100 or 600. So if your structure is very long, so it affects your effective bearing length. So you need to take the least of the 3. So in this case, the least is 600. So 600 times concrete grade times 40% or 0.4, then times your bearing width, net bearing width, and convert. This is for conversion to meter. So this is in kilonewton per meter. So there you have, there you get your ultimate bearing force. So this is your ultimate bearing force, which is 407 kilonewton per unit component of slab. So I hope you understand this and you can do it yourself. And then have a try on it so you can get the grasp of it, the flow of it. So overall, we can sum it up. First, you calculate the ineffective bearing length based on the specification of your components. So you have your supported, and this is supported IST. This is your supporting supporting. This is your, this is the supporting member. Supporting member, supporting SG, supporting member. This is your supported member being supported. So the floor is being supported by the beam. Gives you different value based on the criteria, and then you calculate the clear distance between the faces of support, so that you can get your constructional inaccuracy or delta. So how much you will need to allow for inaccuracy. So for example, in this 17.6, which is more than the minimum. If it is less, then you need to take the minimum. And then once you have these three, you can calculate your net bearing width. Net bearing width, you need to, this is given, nominal bearing length, nominal bearing width. So you minus your ineffective value, then you minus your tolerance. So you get your net bearing width. Once you have that width, now you want to know your length. So the length is taken between the three, the actual length or half of the member plus 100, so 100 or 600. So basically, usually you are taken as you taking it as 600. So you multiply all the components using equation 8.1. So you have your 0.4 FCU, and this is your effective bearing length. This is your net bearing width. This is conversion units, and then you get your, very simple. This is just to design your your beam. But if you summarizing it, what you look in overall, you are currently determining the forces. Usually in designing, we are designing, we get the forces first, then we design the dimension. But in this equation, the dimension come first. So we want to find the forces. It is beneficial if you are designing a components with the ultimate bearing. You are designing a component, so you are giving the specification to the designer. Let's say you are designing a hollow core slab or a beam, a precast beam. So you say that this beam can carry a bearing capacity of 407 kilonewton, bearing force of 407 kilonewton. So this flow of calculation is beneficial for that. But you are designing on the other way around, you get the load, and then you are designing your components. So it's the other way around. You get the load first, and then you specify based on your the criteria here, 0.4 divided by the load. So you get your area, you get your area required. So you get, this is the area of bearing, area of compression. So it helps you specify how large, what is the dimension of your bearing. So that will be all. Next, we're gonna take a look at concentrated loads in bearing. So do the exercise and submit for proof of attendance. Thank you. See you on the next video.